All right, well, let's extend our conversation of functions to talk about a similar idea called sequences. And as you can see from your paper, a sequence is pretty simple. It's just an ordered list of numbers. There's something special about how you get from one number to the next. It could be something as simple as 2, 4, 6, 8, 10, and so on. And it's made up of two parts. Now, this is where you have to actually pay attention because the two parts are really similar. There is the term number and the term. And although they sound really similar, they're actually two different things. So the term or the terms are the actual numbers that make up the sequence. So the numbers that you see listed. So in this case, the terms are 2, 4, 6, 8, 10, and so on. The term numbers are actually number the location of the term in the sequence. So where does that term sit in the sequence is what the term number determines. So if you look down here, I have it labeled out for you on your paper. The term number is the place in the list, while the term is the actual number in the sequence. So we said before 2, 4, 6, 8, 10. Those are our terms. Those actually make up the sequence. The term numbers are 1 for the first number. That's the number in the very first spot, which is 2. The second number is 4. The third number is 6. The fourth number is 8, and the fifth number is 10. So ultimately, what you want to be able to do is take these numbers right here, do something to these numbers to figure out what the actual term would be that sits in that spot. Let's take a look at a different example, and hopefully you will start to see some connections between these sequences and the functions we've been working with. Amazing. So first, it says find a rule, and remember a rule is just an equation for the sequence 5, 8, 11, 14, 17. So the first term is 5, the second term is 8, the third term is 11, and so on. And now, just by looking at that little bit of the sequence, it says it's obvious that the next term will be what? And hopefully you said, go ahead and say it, don't be shy. It should be 20. Because the most obvious pattern that you see is, and just think, how do you get from 5 to 8, 8 to 11, 11 to 14, and so on? What's happening? And hopefully you're thinking, oh, well, that's pretty clear. The most obvious pattern is we're adding 3 every time. And we'll say we'll add 3 to the previous term, which just means the number that came before it. Previous is immediately before it. So if I take the previous term and I add 3, I will get the next term. Now, if you use this idea, let's say to find, I wanted to know the 50th term in that sequence, and we use this idea, what would we need to know? Well, if we just continually add 3, in order to get the 50th term, we would have to know terms 1 through 49. That means we would have to keep doing this, add 3, keep adding 3 every time until we get to the 50th term. And that does not sound fun. So we want to look at what's another possible relationship that might exist in the sequence that would help find the 50th term. Well, if we could find a relationship between the term number, which in this case is 50, and the actual term. That's what we need to know between the term number and the term. So basically, we want to do something to the term number of 50 to get whatever that term is. Now, if you look below, we made a little table here. The term number is on top, so this is the first term, second term, third term, fourth term, fifth term, and so on. And then the actual term in that sequence. So 5, 8, 11, 14, 17, we kept going on, 20, 23, 26. So we have the first 8 there. We don't really want to continue doing this because that'll take a while and that's a little tedious. So now we have to start asking ourselves, what can we do to the term number to continually get the term itself? So we're going to go back to our good friends, variable x and variable y, to represent these. Now, this is a lot like an input-output table. The term number would be your input, and the term would be your output. So what can we do to these numbers that will get us these outputs right here? So that means the term number is going to be represented by X, and the term will be represented by Y. So now, let's think back. How did we do this when we had a function, an input-output table? The only difference is this table goes across, whereas our tables before went up and down. So let's just use the same thing we learned. If these outputs are continually adding 3, remember, repeatedly adding 3, and we all remember that repeated addition is the same as what? That's right, multiplication. These inputs are going up by 1 every time. So as the inputs go up by 1, the outputs are going up by 3. So do you remember where, whoops, wrong number. Of course, it's on the very last one. How about that? If you are adding 3 repeatedly to the outputs, where in our rule did that fit in? And I'm hoping you just said the magic word, which is one of my favorites, the coefficient. So this number right here is going to be our coefficient. So our rule or equation is going to be something like y equals 3 times x. The coefficient on the variable x is 3 because the outputs kept going up by 3. Now, we should be adding or subtracting some number here, our constant, and we know a way to figure out the constant from before also. We used the y-intercept to find out the constant, and that y-intercept, every time we had a y-intercept, there we had one thing in common on the actual ordered pair, and that was the input, or the x value, was 0, and then that determined the output, which happened to be our y-intercept. Well, go look at your table. Do you have an input of 0? And obviously the answer is no. We started at 1, 2, 3, 4, 5, because it wouldn't make sense to say, oh, yeah, the 0th term in that sequence is whatever. That doesn't make sense. However, we can continue the pattern just for the sake of getting our rule. Let's suppose we put in the 0th term number. Then what would this number right here have to be if we are going to continue this pattern, even before it, not just after it, but before? So that means whatever this number is, we would have to add 3 to it to get 5. So what would that number be? And hopefully you are saying it would be 2. So that would mean, same idea, the input of 0, which is the x value, and an output of 2, which is the y. That right there gives us our y-intercept, which means if we graph this, it would hit the graph, the y-axis, at 2. All right, now we have the rule. You can even check it real quick. Let's try 2. Let's plug in 2. If I plug in 2 to this function, or this equation right here, I'd get 3 times 2 plus 2. 3 times 2 is 6 plus 2, and that gives me 8. And what am I supposed to get? I'm supposed to get 8. That means I am right. I could try another one. Let's do 5. Y is equal to 3 times 5 plus 2. 3 times 5 is 15 plus 2 makes 17. And what am I supposed to get? I'm supposed to get 17. So I could keep trying this all day, and it's going to work every time. So now, check mark that one. If I needed to know the 50th term, that's my input, that's my x value, so I'm just going to plug that into my rule, which is right here. So my rule says y equals 3 times the input, which is term number 50, plus 2. And then 3 times 50 is 150. Add 2 to that, and I know quickly that the 50th term in this sequence is going to be 152. And there you have it. Not too much different. Really, the main difference is the way the table is written and the way that your outputs are written, because they're written just as a list of numbers, a sequence, rather than in an input-output table. So use what you have learned from functions, apply that to your sequences. The rest of this is on your own. You do need to fill in your table to determine to fill in your table as many as are available, and then it'll ask you for a particular term. Maybe the 50th, maybe the 30th, maybe the 80th, who knows. You use your rule to come up with that missing term based on the rule rather than continuing that pattern over and over and over again. All right, there you go. Enjoy it, love it, and let me know if you have any questions. Bye-bye.